Hi there guys, welcome back. Right, we're not doing Range Rovers today, and we're not doing weird communication stuff today. We're going to look at something different. Going forward, the idea is for this channel, I want to get regular posts up for you. So we're trying to get them done on Fridays at the moment. That may become difficult as we become busy. For example, next week, we're all out on site on Thursday, Friday, so we won't be getting a video next Friday. But we want to look at some other things as well. A lot of you that are following are interested in the electronic side of things, and for some time we've wanted to look at building a machine from scratch. Now, if you look online and look on YouTube, there's plenty of people building their own computers from scratch. I believe the 8-bit guy is doing his own machine. And I know that there's at least one more. I'm trying to remember the name, but it's completely escaped me now. We're going to do this differently because I want to do this. I will be learning and trying new things as we go. I always used Motorola processors growing up. I started with the VIC-20 onto the Amiga series machines, and then eventually we jumped to 486 based PCs. So the Z80 is completely new to me. However, if you take away the Commodore 64, and yes, I know some of you are going to start arguing, the Z80 is the most common CPU out there. It's also still in production in various forms. You can buy a Z80 off the shelf, or there are embedded versions of it. For the best part, the 6.5 series, not Motorola, MOS CPUs have gone. There are some derivatives around, but most of the peripherals have gone. And it's covered in spades by a lot of other people. The Z80 is quite simple. The basic Z80 machine consists of processor, ROM. You don't need much more than that. Obviously you need power and clock, but that's the basics. Whereas you need a little bit more to be going on with the other processors. So going forward, we're going to look at each block of the machine. We'll break it up into individual units. So we'll look at the processor to start. We'll then look at memory. We're going to treat ROM and RAM at the same time, because I have an idea on how to make this easy to program, but we need to consider how the older systems would have done it. We'll then start looking at peripherals. So we'll look at a rather bent UART there, and counter timers, and hopefully we can build an entire thing up. I do want to go as far as video. Video is completely new territory for me, and I want to try and keep this with as feasible as it is, with parts that would have been used in these machines. However, I'm not going to go mad on making it period correct. When we look at the CPU, I'm going to be looking at Atmel microcontrollers to work alongside it. So we need to bear in mind that we're going to need to look at things like USB to drive that. If we're looking at video, then the machines of this era would have used composite. We're going to need to look more towards VGA. DisplayPort and HDMI, just not going to happen. So we want to keep it simple. We will work with through-hole where we can. Any printed circuit boards that I have to produce for this, I will make available, and we'll try and make it modular. So you've got a backplane with a processor, a backplane with your memory, a daughter board with your UART, a daughter board with your video, and I want a complete system at the end of it. We'll be looking at things that aren't often touched on. We've got a Z80 CTC here, so we'll look at using timers for periodic interrupts. We'll touch on multitasking. Yes, that's going to be fun on a Z80, but it can be done. We've done it on low-end PICs. And that gets me on to the next thing, is why we're not using microcontrollers for this. We could use a microcontroller and we'd have all of this in one chip. We can't change any of it. If we decide we need more counter timer channels, we can't just add another counter timer. If we decide we need more serial ports, we can't just add a new serial port. We want to look at the basics, because once you understand how all this goes together, these concepts do apply to modern machines as well. Your CPU this CPU here has an address bus, it has a data bus, it has control signals. The CPU in the PC that you're watching this on, or the phone you're watching this on, has the same architecture. It still has memory, it still has peripherals. So this is still applicable, and hopefully you'd be able to take everything you learn from this series, provided it all goes through, and apply it to a more powerful chip. The next logical step up would be the Motorola 68000. Again, commonly available still, as are a lot of the peripheral chips. So going forward, we're going to look at each one of these elements, what they represent, and we're going to have a quick talk about how we plan on going about it. The ethos is this, is I want to make this simple, and I want from the very start for you to have a working system. So this is very much just setting the ground. I'm going to go straight onto the CPU, give you a quick crash course on that, and then we'll touch on the other parts on other videos. Hopefully I will film this all in one chunk today, and we can break it up into bite sizes for you, and we can go back on some of the material when we go and do the modules. So I'm going to take these away at the moment. We're only interested in one of these. These are all recovered, by the way. If you are breaking up old electronics, or you have old electronics, especially anything that does any form of processing, you will quite frequently find the Z80 and their support chips in them. We have an old fire alarm panel here from about 1984, and a telephone exchange board here from the late 90s. These have been raided for parts for this. It means that getting the parts is easy, it's not too difficult. The Z80 may pose a problem, I'll get onto that in a minute. But we want to do this as cheap as we can and as easy as we can. Now, if we go down to the heart of the matter, which is the Z80 processor itself, and excuse my drawing, that's our Z80. What we need for this to work before we go anywhere is a voltage, a ground, and a clock signal. At that point, 90% of what you need to satisfy for the chip, other than pull downs and things like that, which we'll cover when we actually get to building things, is done. So that's it, that's your basic circuit. That chip is now happy. It won't do anything. What it does do when you turn it on may be completely random. So what we have on the chip is two buses, and by a bus it's a collection of signals. So we have the address bus, which I just need to check because I'm learning as we go on, and I can't necessarily remember all of this. So our address bus runs from A0 to A15. That is how our processor determines what device it's talking to and what function within that device is. I will try and keep it simple. So this is the locations where things are. Excuse me. And then we have a data bus, which is D0 to D7. And this is, as it says, actual data. So if we ask, thank you Java, if we ask an address, well, what is in a particular location, that data will come back on that bus. If we want to write to the location, we send that data out on that bus. And then we have, along with this, a series of control lines, which we'll deal with later. These mostly are whether the chip is reading from memory, whether the chip is writing from memory, and there's some special source stuff to do with DMA, which we will need to look at because that's how we plan on getting control of the chip. So, most basic machine, we have our two buses. These run like that, and then we have our control buses. Run those across the top like that, and we will generally have some ROM. ROM, read-only memory, is exactly what it says it on the tin. Addressing works slightly different with these, but again we'll cover that when we actually cover the individual chips. So we can read that memory, we can't write it. An example of ROM memory is an EEPROM, which is one of these here. You can see we've got a little window on the top for programming. And bear with me, I'm just going to zoom down just a little bit and try and do this so we can still see my bit of paper. And I think it's actually focused. Yes, cool. ROM is generally where the stuff that doesn't changes. So on a machine like this, your operating system, or at least a bootstrap, will live in here to get the software loaded, or tell the Z80 how it needs to access disk controllers, displays, how it talks to the outside world. We're going to look at doing something funny with this to make it easy to program, but for all intensive purposes, we'll consider this ROM. That's it there. You have a working machine here now. In theory, if you're only going to work with registers, which are small bits of memory inside the chip, and you're working on very, very simple code, then that's all you need. Although you have registers in here and you can work with them, you can't store any amount of data in there. So if you need to store any amount of data, you're going to need RAM, which is random access memory. And again, this connects to all three buses. And we have a RAM here. There we go. There's a RAM. And we'll chuck our Z80 there. RAM is exactly what it means, what it says on the tin. Again, like the ROM, you can write to it, you can read from it, and there is no particular pattern on how you do that. And this can be accessed by the processor. There are ways of accessing it from other devices, which is DMA, which I touched on briefly. And we can store our program data here. If we're bringing stuff in from the outside world, we can store that there to work on it. If we're drawing a display, then we can use that as our display memory. And that there gives you a fairly comprehensive and fairly reasonably powerful computer. There's a tiny little bit of logic you'd need to make this work, but eventually that's it. Not enough though, because this machine can't really talk to the outside world. You can add, for example, on here, pick up these buses again. And the control bus here, I'm oversimplifying quite drastically. Like I say, we will cover that later. You could add a PIO chip, which allows you programmable input-output, PIO, or you could just add some Jelly Bean 7.4 series logic and then bring data in or out. So there we go. I don't have a piece of 7.4 series logic, but I do have a general sort of PIO controller, so we'll drop him there. So we can get data in now, we can get data out, we can process the data, we have software that tells us how to start, and we have our processor. We're still not really talking to the outside world. I mean, the PIO here could talk to an LCD display, one of the LCD display modules, which I don't have. But ideally we want to talk to something else. So we'll use another chip here. And again, we're keeping this basic, called a UART, or a Universal Asynchronous Receiver Transmitter. And again, this is on our bus here. Now, if you want to think of the modular approach to the computer, you could be thinking of each one of these as a separate card. I don't think we'll go that way. We may combine some of them, but in the interest of keeping it small and simple, we may do. We're not going to be running at high clock speed, so we're not worried about lots of connector problems. Our UART sits there, and in the case of this one, gives us an RS-232 serial port at TTL levels. So that's 5 volts rather than the 12 volts that TTL works on. If you then use a USB UART, like PL2303, or the well-known FTDI chips that drive people to apoplexy, you can now connect this to your PC and you can see what's coming out of the UART. So you've now effectively got your display. It's one of the methods we will attempt to use. We're going to get a bit clever with the CPU board to do this, so we order that we can do things without necessarily having all of the items here. For example, I want to be able to run the CPU up without anything, which means we need to do a little bit of simulation. And then we can carry on adding things to it. So we can add the CTC there, which gives us our counter timers. We could add some more EEPROM up there. You know, a little bit more RAM maybe, you know. We can keep going on this within limits for quite some time. Most of the early 8-bit machines were very simple. And in fact, for the best part, the most common machines, like the Sinclair ZX80, that's essentially what you had. Some of you that use these machines will remember such things such as blanking when you were typing, and that's because everything is being done by the processor, including the video. So you can't do more than 2 things at once with that system, the way it was set up. So that's why you got your screen blanking when you typed. So let's just move these out of the way, and we'll go back to the processor. Right, so we have our Z80 here. Now, the normal way of doing this, and as you'll see on most boards that use a Z80, is an EEPROM. On some you'll find a flash chip. And this holds our program, this holds the information on how we get started, what the Z80 needs to configure, how to set the UART up, where the memory is, and basically everything that's needed to get the system started, and it contains your program. If you've worked on PCs, you'd have seen these that often contain the BIOS, which is the bare minimum to get the machine up and running. On most of the 8-bit machines, the entire operating system basic was on here. Then you'd quite frequently have another one for the character generator and for video, and sometimes you'd even have a third one for other things. EEPROM memory was cheap at the time, or cheapish. SRAM wasn't. There are different types of memory. We'll go on and deal with memory later, and we'll cross that and explain why we're going the route we are. So the problem is you write your program, you burn it to an EEPROM. So there's your code. You then need to burn that to that EEPROM and then pop it on your board with your Z80. You run it, it doesn't work. You then need to come back down here. You need to pop your EEPROM. Oh, that's really poor. Under some UV light to erase it. You change your program. You burn it to the EEPROM and you repeat. That cycle takes a few goes, and you need obviously a source of UV light here. And it has to be the right kind of UV light. And here you need a programmer. The life of these chips is finite. The odds of you killing one in this cycle are fairly low because you'll get bored way before that chip fails. However, this entire cycle can take a good few minutes. Everyone that's working on machines now is used to the changes in a program taking seconds. Larger programs, yes, it takes a bit longer, but obviously the same thing would happen here. For example, if you moved your program out onto 2 EEPROMs, you've got to repeat this cycle twice. So we want a way of avoiding to do that. So the plan is, and this is just a plan, we may not go this way. This may not even work. We're going to bring in some modern help. And most likely we're going to use an Atmega Micro. Some of you that have worked with Arduinos will already know some of the chips involved, and that is very much what I want to do here. I want to make this Arduino compatible so that you can use the Arduino IDE to change the code on this chip. We are then somehow either going to get TTL or USB out of that micro. TTL is the easiest way to do. It requires a lot less work and a lot less massing, and is simpler. It's limited in speed. However, the idea is that we shouldn't really be doing much. on our chip we have the address bus and we have the data bus. And the hope is to sit our Atmega on that bus as well. And then we have various control lines. So one of the control lines we want to generate is the clock and the reset. And obviously we'll give a way of resetting it on the board as well, because you might not always have that there. Now this is where it gets a little bit fuzzy, because I'm not knowledgeable in the Z80. I'm learning as I do this. But the plan is there is a line on the Z80, bear with me because I've just forgotten the name, called Bus RQ. Now this is used along with another line called Bus AK to do something called DMA. So take a transfer from a disk drive. We want to set the disk drive controller up, bring it all in, and there's two ways we can do this. We can do what's called programmed I/O, which means our Z80 will go to the controller, say get the data at this address on the media, or this track, or this sector, or whatever the media uses to indicate, and return it to me. The Z80 receives that data, the Z80 then moves it out into memory. That's a lot of operations. So DMA is designed so that you can then say, right, okay, I want all the data from this place on the media to this place in the media, to this place in RAM, to this place in RAM. And then that device can say, right, okay, give me the bus, which is what these two are for. Once DMA starts, the Z80 ceases to exist and your transfer to and from memory goes on in the background without the Z80 involved. During this, the Z80 is off the bus. The Z80 is not talking to anything. It's generally not doing anything. But it can do that operation going directly from the controller to the RAM a lot quicker than it can going through the CPU. Generally, that can cause problems if you're using what's called DRAM, because the Z80 looks after refreshing DRAM. We're not using it, we're not worried about it. But what it means is our Arduino can drive Bus RQ. The CPU will see that go high, and as soon as it finishes its operations, it will drive it back to say, yep, bus is yours. At which point we now have control over this bus. Now, along with some of the control lines, this is the way I want to go. So if we put our memory in there, we can now directly access the memory. We can now directly access the CTC. We can now directly access the EEPROM, and we can directly access the UART. So the Z80 in this situation is gone, and our Atmega is control of the bus. Now, this means, and this is the idea, this may not work, instead of having ROM, we can use a bit of RAM. We start our RAM at address 0, which is where the Z80 expects to start, and we can use the Atmega to program this memory. So again, I'm no artist. And this has all gone horribly wrong here. I will provide schematics and things there. So we can read and write this memory. Now, we can also use the Atmega to keep an eye on the control signals as well, and indeed act on the control signals. These control signals do go around to the RAM and everything else. We mentioned them previously. So at the point that we stop the Z80, we don't know what's going on in the Z80. We can infer what's going on. In theory, there are ways to actually stop the Z80 dead and examine what's happening on the bus. We're not really worried about that. There are Z80 emulators that you can use to play with, and I will cover that later on. But at this point, we know what the control signals are. We've got control of the bus. We can continue to have control of the bus, and we can write the RAM. So we can then upload our program straight into memory, let the CPU out of its suspended state by releasing the bus request, and then reset the CPU and our program will run. We could, if we really wanted, and I may do it, add a battery as well to the SRAM. SRAM uses very, very little power. So what we may do is go down for a system where we have 2 SRAMs, one of which is not battery backed, one of which that it is. And that means that your program can stay there. From this point, actually adding an EEPROM programmer card would be fairly easy. But the other thing that we should be able to do is we're driving the clock, we know what speed the bus is running at. We could potentially fudge our UART in there too, which means one less piece of hardware. I'm wary of doing that. It may be something we do as a debug option before we look at the UART card. But what I'd like is for you to be able to pull this connector out and take it somewhere and actually use it for something. It would be nice to see these getting used for things. This also opens another interesting possibility, because this card, this section of the card here, could be paired up with an older board like this, and you could actually use this to test and probe board and see where the memory is, potentially chase down faults, and actually play with older boards like this. So that's probably something that we'll use as a starting point. Unfortunately, this board has been quite comprehensively torn down. I wish I hadn't now, thinking about it, but yeah, hindsight and all that. There is a device very similar made by Fluke. I believe it's the 9100A, which has different versions of this board that allow you to go through test arcade games and things like that. It's an expensive bit of kit, it's a rare bit of kit, but in theory this should be compatible enough, provided that obviously your board isn't going to be using those lines, that we could, if you are, I'm losing myself my own design here. So if we're using these lines to stop the CPU, then the CPU, the host CPU is stopped. We will actually have a real Z80 there, and we can get an idea of what's going on with the board. So it gives us an amount of debug for testing boards. We can then test the RAM, we can test ROM, we can test inputs, outputs. So there may be some use in this for testing old Z80 machines. Who knows? So anyway, we're kind of getting on a bit now. This is where we want to go. My next step on this is we will look at the Z80. We'll look at it closer, we'll look at the pins and how to connect it up. And hopefully over the weekend I will try and mock this idea up and see if this will fly. If this isn't going to fly, we'll need to find another way of doing it, but it's not the end of it. But the first part, there goes the lorry again. Wait for the camera. Yes, these places are really built that badly. So my first idea and the way to make life easier is to get us to the point where we can run a Z80 and upload stuff to the memory. Perhaps set watches in here so that we can see what addresses are being accessed and when, and get a little bit of software to talk to this. That's going to take a while to do, and there is no particular timeline on us. But once we've got that, and we can get a Z80 talking to the computer, and we can get stuff happening with RAM, then we're most of the way there, and then we'll start looking at how we put this all together. So that's where we're going to go for now, and that's where we'll leave it. RAM we'll cover separately. EEPROMs we may well cover, because this would in theory make a good basis for an EEPROM programmer. You could upload, for example, we've got 256 by 128k RAM there, and I don't think we've got a comparable 1 megabit. Yeah, so we've got two comparable devices there, and you can see the same pinouts. So in theory, if we can get the signals right, you could upload your program, great, your program works, burn it straight to EEPROM. The other possibility is using Flash. Most EEPROMs start with the part number 27. They are compatible with their equivalent RAMs, and there are Flash chips that are compatible with their equivalent EEPROMs. Flash removes the step of needing UV, but Flash needs funny voltages, and that kind of Flash chip's been gone for a while, so we might not be able to do it. But I'll leave you there. That's the plan. That's what we're hopefully going to do, and hopefully we'll catch up when I know that this is going to behave as according to plan. Anyway, take care and catch up with you soon.